A very common tactic in differential equations is to guess the general form of the solution and then plug in your guess to figure out what the specific solution has to be. We will see this later with methods for solving second-order linear equations, and I remember seeing a lot of it in physics where my professors would say, here's the differential equation that models this situation, and here's the properties it seems like the solution should have. So let's try a function of that form and then show that it works. This educated guess and check is very powerful. In our first method for solving first-order linear non-homogeneous equations, we guess that the general form of the solution will be y equals u times y1. But why does that work? Well, let's investigate by taking a look at a generic first-order linear non-homogeneous differential equation, y prime plus p of xy equals f of x. And our y1 is a non-trivial solution to the complementary equation y prime plus p of xy equals 0. We will see why it is important that y1 is a solution to the complementary equation and why it is important that y1 is non-zero. Although you can maybe see right now why y1 being 0 would be bad. If y1 was 0, then y equals u times y1 would be 0, and since our differential equation is non-homogeneous, there's no way the constant function 0 is a solution. In order to make the substitution, we have to find y prime. This is crucial because the product rule works in a very specific way. Each term has exactly one derivative in it. Y prime is equal to u prime times y1 plus u times y1 prime. When we substitute this into our non-homogeneous equation, we get that u prime y1 plus u y prime plus p of x u y1 equals f of x. Notice that because of how the product rule works, only one term has a u prime in it, and every other term on the left has just a regular u. This allows us to factor the u out of the second and third terms to get u prime times y1 plus u times y1 prime plus p of x y1 all equals f of x. Now we can see why it is important that y1 is a solution to the complementary equation. y1 being a solution to the complementary equation means that y1 satisfies y prime plus p of x y equals 0. So y1 prime plus p of x y1 has to equal 0. But we have exactly that expression on the left-hand side of our equation. So we can replace the y1 prime plus p of x y1 with 0, and then the u term disappears, leaving just u prime y1 equals f of x. This is why when we do this method with a specific problem, we always see the u's canceling out. Now we have u prime y1 equals f of x, and we need to isolate u prime so that we can integrate to solve for u. To do that, we need to divide both sides by y1. Remember, we can divide by anything except 0, which is why it's crucial that y1 is a non-trivial solution to the complementary equation, meaning it's not just the constant function 0. So u prime is f of x over y1, so we can integrate and say that u is the antiderivative of f of x divided by y1 with respect to x. So y, which is u times y1, the integral of f of x over y1 with respect to x times y1, recognizing that our indefinite integral will include an arbitrary constant of integration when evaluated. So we can see how the substitution worked, how we started with a very generic form for y, that it was a function that we didn't know times a very specific function, y1. We're actually able to derive a formula for the general solution to the original differential equation.